Welcome to Derived Geometry and Nonlinear PDEs Lecture 2. Jacob, could you take the conference? Thank you.
Okay, yeah, great. Thank you again for the introduction and the opportunity to talk in your seminar. It's really nice. So, okay. So if there's again any problems with my slides, you can let me know. And if any questions at any time, please interject because there's different levels of detail I'll go into. So if you want to probe some more vague statements or hurry me along, then just please feel free to do so. So yeah, so today is going to be a more focused look at the derived and homotopical aspects of sort of this big story that I said last time, which is based really around the two frameworks that we had set up in PDE geometry. One is being this jet bundle approach and having some ambient space that's the universal receptacle of a geometric notion of a PDE and a solution space. And this was this jet bundle approach. And within this approach, we also had the notion of the formal theory of PDEs, and this gave us a lot of tools to understand existence of solutions and to understand their convergence. We didn't really use any of these properties, but it's one of the mathematical backbone of the D-geometric theory that we're working with. So these are important tools. And it should be mentioned that in algebraic geometry, and especially in enumerative algebraic geometry, when someone's interested in counting problems or extracting some kind of numerical data, it's extremely important to be able to make calculations and write things down with, some kind of numerical polynomial. You have Hilbert polynomials for ideal sheaves. Things like this are really, really important. And this is something that is not used so much in the nonlinear PDE theory. But it turns out if you really dig into the formal theory of PDEs, there's algebraic flavor to this geometric and somehow functional analytical story. And from these, you can actually extract important numerical invariants and so like Hilbert polynomials and stuff like this. And you can associate those through this story that I told to ideal sheaves in D geometry. And this is a really important starting point for having a better understanding or classification of certain structures based on the invariance of the problem. So today's story is going to be basically we're going to just talk about derived algebraic D geometry in two they're not competing viewpoints, but in fact, once we start to get into more delicate problems with more singularities, one of them actually becomes a little bit less efficient. There's strict categorical equivalences at most of the stages we're going to be talking about, so this is not going to be an issue for us. And so I should mention first that so today, as opposed to last time, I'll be sharing some results that I've obtained jointly with Professor Artan Sheshmani and Xingteng Yao. We have two articles that treat various aspects of this and setting up this theory in a broader DG derived approach to nonlinear PDEs. And so this is going to be some few theorems mentioned here and there, but in general, the whole theory again is going to be built around some results that I established in my PhD thesis and just some unpublished results as well that I suppose might be common knowledge in different areas of these that I'm talking about, but in this language, surely I couldn't find any references for most of them. So, so what we're ultimately interested in, we're going to have a little bit of a recap of what happened last time and then show the derived objects. So essentially speaking, we are always going to be taking quotient algebras in this ambient jet bundle. And jets of E here means we're taking jets of sections of E is some space, some sheaf, some vector bundle. It can be graded, it can be super, it can, and so it lives over space X, and X can itself also be super. And for physics, this is important, where this is super space time or world sheet. And so, but for us, this is just going to be not super important. And ideally, the situation is that all of our PDEs are nicely, so they're complete intersections of some kind, these quotient ideals, or this is hardly the case, and it becomes even in algebraic geometry, it's hardly the case, and in PDE geometry, it's even less so. So we always need to take some kind of resolution of our equation, our quotient algebra. And in a physicist language, one might call this a causal Tate resolution of the on-shell observables, or the on-shell algebra of functions. But in general, this is really a causal Tate type resolution. It fits into a bigger picture we're going to be talking about today, which is cofibrant replacements. This is a canonical structure that exists in the homotopical framework we're going to be working in, called model categories. And in fact, we want to go beyond model categories and work in the sort of model independence situation, which is infinity categorically. So infinity categories, as I mentioned last time, are just these massive objects with a lot of flexibility and freedom with them. But with that freedom comes the inability to really write things down concretely. So you're resorted to making categorical statements and universal statements. And this is something that you need to get used to if you're working with. So it's quite strange to think, oh, with PDEs, we're used to seeing analytical and concrete expressions for them. And now we're passing to some realm where this is no longer applicable, but somehow this is becoming more natural in the modern landscape of math. So with this structures all existing, our ultimate objects we want to be motivating throughout this whole talk and introducing and studying in depth are these infinity categories that I write in this blue box here. So what does this mean? So pre-stack are some kind of infinity functors from an infinity category to spaces. So spaces, again, is this you can think of as simplicial sets or infinity groupoids. Indeed, this is, strictly speaking, this is the infinity category you get from homotopy localizing simplicial sets along its weak equivalence. So maybe I should mention really briefly that in passing through different stages, we'll be mentioning model categories, as I've already done. So it's unimportant what those are for actually understanding this talk, hopefully. And model category for us is going to be just some really nice homotopy theoretic environment. And the most important point about it is that there's a distinguished class of morphisms that exist in here. And these are these so-called weak equivalences. And so essentially speaking, these are what we want to be viewing our objects as equivalent up to. So we'll say they're the same if they're weak equivalent. And typical examples are quasi-isomorphisms of chain complexes. And these are actually going to be the weak equivalences that we are studying underlying most of the objects here. But in this model category structure, you have more structure available, which is other classes of morphisms, fibrations and cofibrations, and they all interact in a certain way that is really quite convenient. So model categories obviously have great benefit and use, but there's some drawbacks, like there's not such a good notion of model functor, the same way there is infinity functor. There's Quillen functors, which are a sort of analog or a candidate notion of this, which is the ones that sort of preserve a certain class of morphism. So there's left and right Quillen, and this is, again, unimportant, but it should be mentioned nonetheless because this is the underlying mathematics for what we're talking about. So when I talk about a homotopy class in an infinity category, and maybe this is an abusive or non-standard terminology, but it means we're studying the equivalence class of an object, and we can view it in the homotopy category of an infinity category. Okay, so what is the homotopy category of an infinity category? Well, it's a ordinary category, not infinity anymore. Obtained from the infinity category, it has the same objects, and its morphism space of morphisms is defined as the connected components of the space of morphisms in the infinity category. So if you think about it being a simplicial set, you have 0 simplices. These are just throw a bunch of dots on a page. Those are your objects. You can just mark them. And then you have maybe 1 simplices. These are 1 morphism, so arrows in the category. And you can go 2 morphisms. Think about it this way, and then these fill in faces, and these faces that you would fill in as you're triangulating the space of all morphisms can be thought as homotopies between the edges, and you get this big simplex. And this is a really nice way of thinking about infinity categories. You have all these relations tied together. Taking the connected components is, we're just going to be looking at the weak equivalence, well, basically weak equivalence classes, so which of 1 morphisms in these ones. So this is essentially what the object is. Formally speaking, it's obtained as some kind of adjoint from embedding the 2-1 category of categories into the infinity category, or the big infinity category of infinity 1 categories. It's very abstract stuff, but Lurie did a fantastic exposition of all of this and developed this language. And the important point for us is, so this base category here, COM, this is commutative monoids, so commutative algebras, in some infinity categories of D modules. And these are going to be concentrated in degrees less than 0. Terminology for this is going to be connective. And if you have these algebras and you take the infinity category of all of them, so we've done this. We started with a model structure, now we're into infinity one. Taking the homotopy category, as you see here, is just, it returns to us the model category structure, and all of the quasi-isomorphisms, the weak equivalents that we singled out, they're inverted. So we are formally adjoining the inverses. And so this is what we mean by things are equivalent up to this class. Okay, so the 2 realizations of the picture we're going to talk about are this D versus Derived. And I'll say what this means more. And it really comes down to the fact that connections and differential operators can be encoded in 2 really standard ways. Actually, if you come from differential geometry, maybe action of differential operators is more familiar than this Derived one, which is sort of a quotienting of a formal groupoid by this infinitesimal symmetry relation. So what it means for 2 points in a algebraic variety to be infinitesimally close together. And in fact, it's really quite a nice analogy, because this infinitesimal closeness is related to the notion of connection in differential geometry, which is the underlying structure that a D module generalizes. Okay, so we'll look at the 2 of these, and we're going to be studying this derived enhancement. So these derived D stacks. Oh, so this category here, these pre-stacks. So when I say pre, it means we're not imposing any descent. So it's not really a homotopy, higher homotopy sheaf, infinity sheaf. We just want them to be functors, so functorial. And here, there's no algebra A that we're slicing over. So the slice, the reason for this is because essentially, if this is our algebra A, we need to be passing to some quotient category. So we're looking at quotient algebras under A. So this is was built into our definition last time of these ideal sheaves. You had these sequences IAB, which I'll recall again, and this is really the reason for passing to this. Okay, and then we essentially are going to be studying these objects that we can work with, infinitesimal geometry on them. So they have this notion of cotangent complex, and this is the derived deformation theory and deformation obstruction theory for these. And so last time I mentioned this sort of bicomplex. We're going to go through this really quickly again today, and then it's derived enhancement to cotangent complex. And if you look at the whole derived algebra of this, which is a standard thing to do in derived geometry, we end up with some tricomplex. So this is just quick picture of what we're going to see today, this variational tricomplex. And so each colored face of this one that I've shown so far of this big cube is a bicomplex in its own right. Each one sits in a cohomological degree. So remember, our algebras and everything are going to be starting in, well, basically they can be an infinitely negative degree, and then we're working in a cohomological convention. So differentials always go +1. So they all go from -2, -1, and they hit 0, and we don't have anything after that. So this is why this blue one is sort of the classical one that we see, and we're going to progressively go into the page. Well, we're coming out of the page technically, but quasi-smooth mentioned here is the sort of closest thing to being smooth in the derived world, in the sense that you have smooth data in degree 0. And this is actually made very precise in derived geometry. And then, and we'll see this as well. And then you have the -1, it has this bit of derived degree, and that's it. Okay. So let's recap really quickly what's going on. So a kth order nonlinear PDE, YK here, is in some tower of jet bundles, and it's a submanifold in the K jet space. So jets K and M here is, remember, N will be our amount of independent variables on the base, X and M are the sort of fibered ones. So in these spaces, we're going to be imposing our PDEs on this E, these coherent sheaves. This is sort of the rank or the dimension of the fibers. And then we wanted to prolong this and have no obstructions to doing so, no obstructions to the existence of formal solutions at each level. And this means that this whole tower actually is a tower of surjective submersions. And then this was the formal integrability requirement. And then there was this involutivity requirement, which basically says at some point also in this tower, where after differentiating, and we're not going to get any more variables, we're not adding any new ones, and then we're not going to have any more differential consequences, new consequences. So essentially our system is completely like consistent, and it has as many as it's going to get. It also ensures that with these two requirements that our algebras, the D algebras we get in the infinite jet level, which is the projective limit of this thing, is going to be non-empty. So that was the formal theory, and the structural elements of these spaces. So when I don't write a subscript anything here, so I don't think we really work in the finite dimension, a finite level anymore. But so this is some, it lives inside of this jet's infinity. They had this connection. This was the Cartan distribution. They're spanned by these total derivatives. Now what's interesting, actually, which I might have wanted to mention last time, just for a curious thing, is people have sort of thrown around what should be the so-called Defayeti dimension, because it's infinite dimensional as a manifold, but maybe we call it, the dimension should be the Cartan dimension. And so people have found a lot of heuristic analogies by declaring this dimension of a Defayeti to be the dimension of the Cartan distribution. So in the case of a base manifold of N, it's the dimension of the tangent space spanned by these. So it's N, it's N. But what's interesting, and I think a bit for homological considerations, is to redefine it as the global homological dimension of the sheaf of differential operators. They coincide, but in fact, when we're working with these sheaf theoretic properties, one of them, this new notion is more, I think it's more consistent with it or coherent with this theory. So anyways, we are essentially looking at D affine schemes. So affine D schemes, which are defined to be the D spectrum of these commutative algebras. So the opposite here, and the functor of points approach that we discussed last time. So what's at this, viewing them as these kind of spaces. Well, we can call them just algebraic spaces, and these are higher spaces, and then these are the infinity spaces. So here, this is just the functor of points. We view it as with an underline. So it takes B points. So we'll call this a B point of Y. Is just mapping, probing this space by spaces of a similar kind. Dually, it can be viewed as taking functions maps of algebra morphisms from the functions on Y to B. So you swap them around because we're taking the opposite, and this is covariant functorially. So a t-geometric nonlinear PD now, remember, was a sequence like this, IAB. And I is going to be some D ideal sheaf. So it's stable under the action of differential operators. And we wanted the solution spaces for them to be they don't take up the whole solution space. So this is, they're just not trivial. And then we don't want them to be empty so that they're consistent as well. So from this data, if we impose the additional constraint that this is a short exact sequence, well, we end up having an embedding here of D scheme. So this can be viewed as another geometric way of this algebraic IAB kind of portrait. And so, as I mentioned before, from the first slide, we're taking these quotients, they're going to need resolving. And from the point of derived algebraic geometry, if we want to look at differential forms on the quotient, so this guy, we're going to be essentially, they are the Kähler construction of ordinary one forms, bilinear one forms we saw last time on the cofibrant replacement. So this is going to be sort of the rigorous definition for the cotangent complex of a D space, is in terms of its resolution. And then we had some nice finiteness conditions on all of these objects. We saw D formally smooth and D smooth, and our objects all interacted nicely with the jet functor. It preserved them, so it sent O formally smooth to D formally smooth, and so on. So this was a really nice thing that it becomes more important as we go to the infinity categorical level. And actually is retained in this level as well, surprisingly. Okay, so, well, for some classes of morphisms, which we'll discuss. So D finite typeness wasn't made such as explicit last time, but it really corresponds to these D schemes that are freely generated. And so D tensor E here is going to be, this is a functor of so-called induction. So you take the induced left D module. It means just tensoring some coherent sheaf. Oh, so this should be E here. Some coherent sheaf of OX modules on X. You just tensor it with the ring of differential operators. So there's a left and there's a right induction, depending on which side we tensor it with. And this, as I mentioned last time, this D module theory, the left and rights are categorically equivalent, made by these sort of quasi-inverse, quasi-equivalent by these twisting of the dualizing sheaf. And this is again important later, especially for the infinity categorical setting when we pass the Durham spaces. So another special case of interest, which is something that we will be discussing today actually, is what happens if we take these symmetric algebras. So it's a nice way of producing for free D algebras from D modules. So last time we saw that if A is the symmetric algebra of a D module and the D module is projective, then A is going to be formally smooth, D formally smooth. It's just a nice exercise in homological algebra, but we saw that a lot of D modules are represented as cokernels of some operator. It can be a system of operators, so this could be a matrix. But here, for instance, if we just take one operator, and if we impose a condition that A is the symmetric algebra of this D module, and we propose this condition. So the characteristic variety, if we recall, of a D module is essentially the zero locus of its principal symbol as a polynomial function in the cotangent space. So the characteristic variety is an extremely important object in a geometric object related to PDEs. And we'll talk about this later because this is one of the objects that we will essentially derive and non-linearize into our setting. And this condition here becomes extremely important. So one of this exercise is you can show that if the solution space for A of this form with this condition, if you take solutions in analytic functions on M, which I haven't defined here, but you can find in any D module book, then it's the same thing as having hyperfunction solutions. So this is a result that's typically called elliptic regularity for D modules. And in fact, what's coming on here how to prove it is essentially a very silly little adjunction. Okay, so D jets and Derived jets. So we're going to talk about this really quickly and then go forward. So we take these DPDEs, and so we're going to use the terminology imposed on sections of something. And this will mean that basically A is coming from some jet construction. And so the jet construction is a more general thing in the sense that it's a universal right adjoint functor at the level of schemes. If you pass to algebra objects, then it defines a left adjoint on the commutative algebras. And so 4 here, remember, is just forgetting the connection. So forgetting this D structure you have. So this is the universal property I'll refer to when I talk about the universal property of jets, or the universal jet adjunction. And this is extremely useful for a lot of reasons, as we'll see. So the D algebra structure is always going to be acting through the lift of this Cartan distribution. Okay, so as I mentioned before, these differential operators, they're not jets. Differential operators and jets have another description via an object called the Derived space, which I'm not sure who it originally goes back to, probably Grothendieck, or I know Simpson had a fantastic work showing this, discussing the Derived space as the stack associated to the formal groupoid that you get by completing the diagonal. So all of this is very algebrogeometric terminology. And what it means is if you take 2 points, you're going to identify them to be infinitesimally close. So this down here is what I write in the algebrogeometric language. So you take 2 R points of a scheme, they're so-called infinitesimally close if when they restrict to the reduced ring structure, they factor through the diagonal. So I is the diagonal ideal, and it means if you pull back the ideal, you landed the nil radical of the R. So it means that if you look at some power of the formal completion, that for some n, it's going to vanish. And this is sort of like the vanishing order. And in fact, this vanishing order corresponds to the order of the jets. So if you take the limit over all of these n's, you should get infinite jets. And so when we're restricting to this formal completion, you can have finite order. But again, we're not going to be doing this because we want to retain our D algebra structure. And as I mentioned last time, if you differentiate at different levels, well, you lose the ability to do so. And so if you're more of a differential geometer, there's a really nice discussion of this perspective by Gates-Goey-Rosenblum in this derived world. They use this terminology, crystals, and then Simpson as well. And then Lurie has this nice crystals and D schemes type short note. And what it really goes through his explanation, which I think is very enlightening, is it's another way of looking at connections in a fiber bundle, is not through lifting vector fields or acting on the fiber coordinates, fiber-wise derivations through vector fields on the base. So this is a typical definition that you would see for a connection, is you have some map from derivations on the base to differential operators of first order acting on the fiber, so fiber-wise linear differential operators with scalar symbol. And then if this map is a Lie algebra morphism, this is a flat connection. But there's an alternative viewpoint, which is through this parallel transport. And this parallel transport is the notion of identifying nearby fibers. And so this is exactly what this formal completion, this infinitesimal closeness relation is representing in the algebrogeometric setting. Okay, so there's this fact that I quote here. So D modules are sheaves on the Derived space. It shouldn't be too hard to convince yourself from what I just said that this is indeed true. So if D modules are generalizations of vector bundles with connection. So if you take a sheaf over the Derived space and you're taking stalks of this sheaf, and you can identify them at infinitesimally close points at the base. This is exactly the parallel transport D module point of view that I just said. So what's important about this fact? This fact transcends the setting that we're talking about now. For instance, X here is a smooth and proper scheme, or a complex analytic manifold. It can even be a smooth differentiable C infinity manifold. And the drum space is more or less defined similarly in all of these settings. But as you go further into the depths of mathematics, you get different drum spaces, most notably recently in this rigid analytic geometry and condensed mathematics. There's different types of nilpotent neighborhoods you can consider. One of them being, for instance, this so-called overconvergent neighborhood of the diagonal. And so this is important for generating new classes of differential operators, maybe ones that have some kind of are related to some trend series, or have some growth conditions, or remember topological information. This is this condensed mathematics viewpoint. So this goes into the derived setting as well. And what's interesting in this one, as we'll see too, is this derived, or this drum operation in the derived setting doesn't detect derived stuff. What does that mean is that if something is derived, so it has negative, like these cohomological degrees that I would discuss, and you got these differential graded structure, you kind of just kill that away. And so this is fine for us because at no point are we going to want to derive the base x. This is for us, it's always going to be classically the space of independent variables, or dependent variables, sorry. And then this, so there's no need for this to be a derived space. But in some situations, you indeed will want this to be the case. But why is this drum space useful? As I said, it's really encodes this notion of connection. And it's really useful for making sense of the notion of a connection on the fibers of something. So in the words I just was saying, it's connections in the fibers of some modules, D module, or connections in the fibers of a bundle. So vector bundle with connection. But you can go further to more abstract objects. You can have connections on categories. You can so-called crystals of categories. You can have connections on spaces, stacks, derived stacks. So this is a very useful thing to work with. So we're going to adopt this terminology for later years. So if we have a morphism of prestacks, just think of them as some generalized functor, generalized spaces. So a connection on Z along this is a map that will write Z tilde, or some resemblance to the original Z, and it's now over this drum space. And then we have this together, it comes with an equivalence here. So the fact that we get something over this drum space is really what's telling us we have this action of this infinitesimal groupoid that's acting on our original space. It's the notion of this connection. And then if this holds, sometimes some people use the words categorical connection, but this is to reflect this is categorifying this notion. But people use the terminology as well, crystal of spaces or crystal of categories. If this Z happens to be a smooth affine scheme, and X is a smooth scheme, then a crystal of schemes over X, these are precisely these schemes. Well, if the morphism between them is affine as well, but this is inconsequential for this discussion. So now the observation is if we have a D space, so originally we have some guy that has already a connection living on it. This can be equivalently recast as a crystal of spaces via a certain diagram. And really, this can be used to detect sections of the original space and what it means for them to be flat or solutions to something. And this means that they are essentially coming from their definition over the Durand space. And we'll see this in more detail later. Okay, so again, we saw this differentially generated objects. These were very interesting for us, and these are essentially were the infinite prolongations of the PDEs. So you can formally prove that a formally integrable nonlinear PDE in the jet space approach gives rise to an infinite prolongation, and this is representable by this is isomorphic in the algebraic category to a D scheme with a differentially generated ideal. And so solutions, again, these are formal solutions, though they're infinite jets of functions, and the graph of them lies inside of our solution space. And algebraically, it means that the dual of the jet prolongation factors through the projection, the fibration of the D algebras that defines our sequence IAB. So we write it here as Q. If you work in the opposite picture, it means that any section of A, of spec of A, is going to be a solution if and only if it when you take the section, it actually injects through spec B. So it does indeed lie in the solution locus. Okay, and this is what we'll call the local solution space or D solution space because it's directly discussing and related to jets of functions. But there's also this non-local solution space, which is defined in terms of those sections of the original bundle, and you are declaring those to be sections if they are, or solution sections if they have their jet annihilated by the ideal. Okay, so if you have a morphism of D schemes, you can define a functor of points mapping space between the two. And essentially, it's just taking U parameterized maps from one to the other. So maybe it would have been better here to write sections because we're doing it the opposite way. But so this is taking U parameterized sections that are additionally flat morphisms or horizontal, people call them. So which means they are morphisms of D schemes. So they preserve all of the action by differential operators. Okay, now sections is just this functor points approach. It's as you would expect. It's U points for some probing space U are those U parameterized sections, and then they project back to the base. So I haven't denoted this condition here, but sections should be understood as meaning that it has this section condition. Okay, and so you can prove that the solutions of, so as we know that OX can be acted on, so functions on the base can be acted on by differential operators just by derivation. So spec of OX is a trivial D scheme. We can take morphisms or sections like this, and taking solution sections of this is equivalent to all the sections here. This is the formal theory basically saying infinite prolongation. You can infinitely prolong a section. And this can be, so this is a formal way of seeing it in this functor of points approach. And this is a consequence, essentially speaking, of the universal property. So you see here, we are passing D schemes and O schemes. So this is a right adjoint and then forgetting the structure. Okay, and then going through again, we have these D schemes, we have the calculus. So local calculus, again, local is meaning living on the jet space. I think it has to do with the fact that in physics, you have quantities that are local, so they depend on fields. So local Lagrangian densities are those that are functions of the fields and their derivatives. So this is the terminology, I guess, that's used, but essentially we're doing sheaf theory. So really there's a different local to global dichotomy happening here, but anyways, local calculus on D scheme. So differentials look like this. We want to study the Derived complex of this guy. So this object has a universal Derived differential defined D linearly in this category of AD modules. So AD is, remember, it's A tensor over OX of the D. And these were interpreted as some kind of horizontal differential operators, so or differential operators in total derivatives. And what's interesting is this Derived type complex doesn't really terminate. And one reason you can see this and convince yourself this is true is because there's infinitely many jet coordinates. And what this is doing is it's differentiating, it's so-called vertical differential. It's differentiating with respect to the jet coordinates. So the coordinates to U sigma alphas, which represent the derivatives of the fields or derivatives of the fiber coordinates in the space E that we're taking the jets of sections of. So it just goes forever. So this is unbounded eventually. So well, we want to study some D-module Derived complex of this. And so this is related to the horizontal characteristic homology of our spaces and contains conservation laws, information, stuff like this. So it can be formally defined using D-module techniques. And what's interesting is this H is sort of this zeroth Derived cohomology of this space. And it amounts to, at least in this very classical setting where things are quite easy to work with, it's taking co-invariance of this D, the action by differential operator. So you can view this as if A is the functions on jet space, so they're of all the X, the U's, the U sigma alpha, so all of these coordinates of the derivatives of the fiber Y's coordinates, then taking omega, the top forms on the base, tensored with A, this looks like Lagrangian densities because we take volume forms and then, as I said, these Lagrangian densities, these local Lagrangian densities on the jet space. And then if we are taking this coinvariance by the dx action, this is representing the fact that they are don't change by total divergences, so action by these differential operators. So this is a physical thing that people know that Lagrangians don't. They don't change the equation of motions by a total divergence. So this is very nice. So objects of this are interpreted as action functionals, as we'll see later. And essentially speaking, we want to study these variational cohomologies. So here I shouldn't have used this notation for I, but I star here is not the ideal. It's the sheaf of integral forms. So I haven't changed the notation here, unfortunately, but this is actually the case of a supermanifold of dimension nm or np, and n is the dimension of the even variables. And so this is the replacement sort of for this canonical sheaf, dualizing sheaf here. You're taking a resolution of this complex, but it's not important. So we can restrict just to a certain horizontal part, which is just the RAM complex on the base, tensored with the functions in the tops. So they look like this. These are called horizontal forms. They're pullback of the RAM complex basically on the base. And then you can generate a complex. It does terminate here at the global dimension, homological dimension of the differential operator. So base manifold at dimension n, it ends here. So this is just differentiating with respect to the Cartan. So these total derivatives, and then you just this is summation notation here. So you just wedge with these. Okay. And then any ideal of our system is we had these generate subspaces, and because they're dx ideals, these subspaces are dx ideals, dg ideals now. They inherit the differential. And the important result in the calculus of variations is really saying that if A is this jet space, these don't have any cohomology. They're sort of a resolution of this constant sheaf here. But in fact, the difference is, so I've omitted the top degree here because today we're not going to discuss the calculus of variations in detail, but this is related to the functionals and Helmholtz conditions and stuff like this. But we want to be deriving this whole complex construction, not discussing its well-known details already. So these are usually not trivial, and the sheaf and theoretic interpretation is that this actually becomes a quasi-isomorphism in the OX modules. Okay, so we get some morphism of complexes this way. So this guy here is the quotient complex, and we just can also write it like this. So it's what's even nicer about this is it becomes a sort of functorial, and you just get, good old homological algebra, but now local in over AD modules, which is somehow quite a nice thing. It's like rewriting these classical textbooks about homological algebra, but now just understanding all of these modules are coming from some jet bundle perspective, mixed with some D module theory. And then you have these typical results that you would get on functorialities of sequences, but now they're not really of complexes, but they're of bicomplexes because we're looking at the variational ones. So again, you take cohomology like normal, and you get some long exact sequences, and then you can study the relations between the invariants that they contain. Okay, so the variational Derived complex is the one we care about. It's not just the Q part, so that was the horizontal, and not just the P part, which is the unbounded jet direction, but both of them together. And for some reason, in the terminology or in a lot of the literature about bicomplexes, the horizontal direction is put vertically, and the vertical one is not. I don't understand why, but anyways, I adopted that convention here. So horizontal ones, as we denote, so these Q pieces are also usually denoted with an overbar. So if we have one PQ forms, it means we have P vertical forms, Q horizontal ones. So here it's 1, 0 forms, or if P is the vertical degree, then it's 0, 1 forms. And then cohomology is taken naturally through spectral sequence. Okay, what's really nice for us is globalizes. If we take an algebraic space, and now just for any functor that's a sheaf for a topology, it's going to be the d-étal topology. I introduced d-étal morphisms last time, but we eventually will, there's a derived d-étal topology to instill once we get to derived algebraic d spaces that are derived d-flat over the base. So you need to just introduce all of these homotopical flatness, homotopical descent conditions. But in any case, it globalizes. And you can show that bicomplex structure still holds. Of course, this one still goes off to arbitrary jet degree vertically. And the differentials act as usual. And étal d locally over x and Zariski locally over the base to x, we have this sort of descent-like limit. So this shows that we can really define global bicomplex over D spaces from the knowledge of their definition on affine spaces. Okay. And then one of the uses of these forms are the definition of characteristic varieties. So if you know about D modules, they're non-commutative rings. You can, they have a filtration. You can take the associated graded. The associated graded becomes a coherent O T star X module, where T star of X is the cotangent bundle. And the object you get is basically, it's a polynomial module defined by the ideal defined by your symbol of your differential operator. You can do the same thing for nonlinear PDEs. Surprisingly, it's a pullback of this T star of X to this jet space or D scheme. And you end up again with some kind of like filtered coordinate algebra of functions on this quotient. And so here I'm just writing filtrations everywhere, blah, blah, blah. And you can do a lot of the same micro-local techniques and D module techniques as you would want. So you can study, you can look at principal symbols, linearized symbols as well, and stuff like this. And one of the structural theorems that is that you have this differential operators, D that commute with the base, dx. These are going to be, these coincide with the A of A tensor D. So these AD modules, this is exactly what this ring is, just more globally presented here as this definition using sheaf theory. And there's an order filtration. It's a differential operator, so that's no surprise. It has associated graded, and the associated graded object is, again, like you would get in the D module situation, is polynomial functions on the cotangent bundle, this modified one, which is just polynomial functions from the cotangent bundle with coefficients and algebras of functions from Y. And then you can show that these forms that we just saw are filtered, and the characteristic variety is defined entirely analogously. So it's the support of the graded module of this guy. It can be shown that all of everything that we just said is independent of filtrations, and all of the usual arguments that are established this is a well-defined notion go through here. So why is this useful? So I mentioned last time that singularities run rampant in the nonlinear world. They have this, for instance, if you want to study certain micro-elliptic regularity of nonlinear PDEs, they fail, and this is propagation of singularity type statements, they fail in the nonlinear one. Reasons are especially that nonlinear singularities have no reason to propagate along by characteristics of these Hamiltonian, the Hamiltonian is defined by principal symbols of our operators. And what can be done to sort of account for this extra information is not just micro-localizing, which is for us means past the T star of X. So we're adding codirections, remembering propagation of solutions and solution singularities. but you want to do higher microlocalization, so second localization, or S micro localization. And so in our first work with Sheshmani and Yao, we discussed this notion, at least set out the preliminaries for the understanding S micro characteristic varieties. So these allow you to have singularities that are maybe restricted along involutive submanifolds of T star X. And the one that we care about is essentially the one microcharacteristic one for certain cases. And it coincides with the characteristic variety in the normal setting, in the usual sense, if we take the zero section of our cotangent bundle, then it coincides with what the ordinary characteristic variety would be. And you can prove that these are invariant under d-isomorphism. So if you have two smooth D schemes, and a d-isomorphism between them preserves the characteristic variety. And this can be extended to prove the invariance of the variational bicomplex in the category of D schemes as well. And then we have vector fields. They're given like this, and they're related to linearization. So we'll take a break in about 5 minutes, and I haven't got into derived stuff yet, which is not ideal, but let's just finish with quickly what linearization is going to mean for us. So typically, analytically, people have said, okay, linearization means linearizing, and they have this formula for it. It means you take some kth order operator, you have a background solution fixed. The linearization of this is going to be formally defined as perturbing around your solution, and then they're taking the derivative with respect to some variable and then setting it to 0. You indeed get a linear thing from it. So quasi-linear, if you remember, is a type of nonlinearity where you have highest you have linearities in the highest order of derivatives, and then potential nonlinearities in lower ones. If you linearize, you get a kth order linear operator, but we want to do a coordinate independent one. So if you have some kth order differential operator, so this is at the finite level, this is a geometric way of understanding linearization. So again, you're looking at all these kind of pullbacks along solutions. You fixed one and you're doing this game that exists. Okay, this is still at finite level, so it's not going to be useful for us. It doesn't help us. We can, of course, if we have a D scheme, we can, and assuming the formal integrability and involutivity, it means we know that everything at some finite level stops, and we can restrict to that level. We lose the D structure, but we can probe the linearization at that level if we want to. So this is fine, but we want to be working entirely invariantly and in a coordinate-free way. The takeaway from this discussion is that linearizations, they are given by vertical vector fields. And a vertical vector field possesses a flow, essentially, or formally a flow. And this flow pushes solutions to solutions. And so this can be used to understand the classification of operators, but in low order, it's done again using principal symbols. So here I've just written in 2 dimensions, order 3 and order 4. And you associate polynomials to this. These are the symbols. And then you probe their behavior by how the roots of these polynomials look. So this is just algebraic geometry. Okay, so you look at the proportional to the discriminants of these polynomials, and you can classify them. So this is very standard ways, but of classifying PDEs, and especially linear ones, you can just say it's a nonlinear PDE, or at least people have done this a lot, is a nonlinear PDE is blank if all of its linearizations are blank. This is also not ideal. And so for instance, and it also is not really applicable to, for instance, higher order cases. These are, you see, very low dimensional, low order operators. For instance, also there's PDEs, nonlinear PDEs that have behavior of a type in one region and not in the whole region. There's also ones that don't have any behavior of these types at all, and some that have multiple. These are so-called mixed type PDEs, and they're very hard to understand. So in this analytic setting, you would say a kth order PDE is elliptic if its linearization at the k jet of a solution is elliptic as a linear differential operator. So now, using this geometric linearization we saw, you can formulate what it means for a kth order operator, nonlinear, fully nonlinear, to be elliptic. So if for every section, this linear guy that we saw from the previous one induced by the differential is elliptic. Again, this is related to vertical vector fields. But again, this is finite level. Can't be treated in full generality. And what happens when these things become derived and have more structure? And this is going to bring us to the type of objects we're going to be treating now. So essentially, all of the things I just mentioned, some natural DG analogs. And I'm going to propose some natural framework for us to handle all of these things. So the tangent complex, the cotangent, or the tangent sheaf, cotangent sheaf, the duality between the two, the solution functors, the properties of finiteness that guarantee us that we have good ability to do calculus on these spaces, the corresponding bicomplex, and then linearization and the characteristic variety and what these can tell. So tell us about the nonlinear PDEs in this setting. So I guess let's take a break now for a few minutes. Does anyone have any questions before we officially start what I wanted to finally talk about? Okay. Let me just... Okay, so now we can finally start doing some what I promised this last 2.5-3 hours of the lecture. And so the last 1 hour of the lecture, we're going to try to go as deep into the derived stuff as we can. So the beginning of the derived D geometry is undoubtedly from the Baylen-Drinfeld chiral algebra story. If you're familiar with this book, they wrote about this one complex dimension 2D CFT algebrogeometric approach, where the D geometry was coined and they worked out a lot of things, but they left open this homotopical generalization to higher dimensional varieties. And so this model structure was established by Gennaro De Brino, Damien Pistallo, and Norbert Ponsin in 2018, maybe, or a bit before that. They wrote a series of papers just establishing this, trying to establish what this homotopical algebraic geometric context, as a term coined by two derived geometers, Bertrand Tohen and Gabriel Vezzelzi, which is basically like a very general set of axioms that you need to be able to do homotopical algebraic geometry. And if you remember, derived algebraic geometry, I essentially defined earlier as algebraic geometry plus homotopy theory. So homotopical algebraic geometry is a very close synonymous term. So they started to go through this, but there's some problems that exist for finiteness conditions and working sheaf theoretically. One of the ones that is a very easy one to point out that I pointed out last time is the fact that dx as a sheaf is not easy. It's not going to be dx coherent if you tensor it with itself. And this extends to a lot of other problems that we want to be doing, multiplying things together at some point, taking tensor products, and we're going to lose coherency a lot. And this is the biggest part of doing derived geometry with this spaces is we need to make sure that finiteness hypotheses are imposed so that our functorialities preserve perfectness of complexes. They preserve some kind of compactness. So compactness is going to be the term. It's the homotopical or infinity categorical or model categorical term for homotopically of finite presentation. And this is all a lot of jargon if you don't know any of this homotopy theory. So at some point, I'm going to, after giving you a lot of it, I'm going to drop it and I just call things nice. And when something is nice, it's basically dualizable in a homotopical setting. It means it has a dual, it exists, and double duality statements hold. And essentially the object itself is perfect, which means usually it's going to have finite dimensional cohomology and even be bounded as an object. So, okay, so this is definitely the start of the story. They proved there's a covariantly generated model category structure on CDGA. So commutative differential graded algebras over D. And they took global sections of D. They restricted to affine varieties, X, and to global sections. This can actually be weakened, this condition, by using a term which is an unfortunate clash of terminology from D schemes. They're called affine or de-affine schemes, defined, I'm not sure by who. It just means that global sections of your, or D modules are globally generated on this affine variety, essentially. So you can weaken this a little bit, and it takes into account also projective schemes as well then. Okay, so how to prove this exists? So the important point here is what I said earlier. The weak equivalences are what we care about, because we're going to pass away from the model structure into an infinity categorical one by localizing them. So essentially, they're the quasi-isomorphisms. So for those who don't know, quasi-isomorphism is a morphism between complexes that induces an isomorphism on cohomology. And the fibrations are just degree-wise surjections. So if you write a complex out as a chain of things, it's just between each term, you have a surjective morphism of the underlying structure. So how to prove this? You can use this adjunction. It means, so they first established that there's a model category structure on differential complexes of D modules. This is exactly the same model structure if you're familiar from just cochain complexes of vector spaces, basically. And then they just use this so-called transfer theorem, which means you can transfer a model structure. It means if you have a class of objects in one symmetric, this will basically transport over, and you can use those same ones on the other side. Okay, this is just the very start. But it's interesting is that compatibility complexes for PDEs in the differential geometric and like formal theory that Spencer, Goldschmidt, Quillen all developed, and Cartan even developed cohomological techniques to understand the causal Tate resolution of an on-shell algebra, so a quotient of a regular ideal that we saw earlier. These are all examples of larger cofibrant replacement functor that exists on this model structure. So some more facts is that you have another adjunction that exists, and you can use this to transport further a model structure to our local modules. Now they're DG. Okay, and so all is the same. So weak equivalences and are the quasi-isomorphisms, and fibrations are just inherited from this free forgetful adjunction. And so we can take derived functors between these. And when you take a derived functor, it means you're going to be, in the standard sense, you're just taking a fibrant replacement or cofibrant replacement. The term for us that cofibrancy means really it's nice. They're nice ones. And fibrancy is sort of like the opposite nice one. So if we're working with spaces, cofibrant, we want cofibrant replacements for all of our algebras. And in fact, the algebras we work with, the DG algebras, they're always going to be fibrant in the model structure, which is just, it's a technical thing that should be noted, but it's not going to be used for us. Okay, and then this is where their story sort of stops. And we come in with the Tohen-Vetzotzi standard approach for defining pre-stacks. So the pre-stack, we want to have some kind of simplicial enrichment. We have CDGA already as a model category. You can take simplicial objects in pre-sheaves. So we're just looking at functors from CDJ to sets. And if you take simplicial pre-sheaves, it means you're taking functors from CDGA to simplicial sets. And again, simplicial sets is the usual model structure that I mentioned before with. But it's the one we're going to be localizing to get to spaces anyways. And then this is all model categorical, and I don't want to stay here very long. So passing to the so-called homotopy localization, it's also left boost field localization, gives a way of inverting these weak equivalences, and we can pass to something called the derived pre-stacks from these simplicial pre-sheaves. So functor of points approach gives another Yoneda type embedding. So we take a space and we view it as a pre-stack, but this is Ho everywhere is because we're taking this sort of derived. It means that at any point we're gonna, when we evaluate our space, we'll be implicitly also putting the replacement functor for all of our algebras, like the cofibrant ones. So at least when I'm talking about model category stuff, it's good to just maybe say let everything be cofibrant, because we don't want to be cumbersome with the notations, and you can make replacements anyways. And so you can introduce hypercovers. These are just a fancy term for descent conditions, and localize these. And it's a longer story, but the point after you do all of this is that we can effectively prove there's an equivalence between localized prestacks over some fixed space and the prestacks localized over, or the localization of the prestacks on a slice site and the slice site of the localization. This commuting of the two has to be proven through equivalent adjunction. And what essentially all this does is verify that we can in fact view objects of a slice category of algebras as honest homotopy classes of functors out of that slice category. And that's what we saw in the very first slide, these functors out of commutative monoids sliced over an algebra. And so to be more zooming in on our objects, the CDGA in concentrated degree 0, they're just a object like this, and it has terms start like ending at 0, I guess, going from like -2, a to -1, and it's complex. So this squares to 0, has a differential. And derived affine D-scheme is defined as the opposite of this category. It's just as usual algebraic or derived algebraic geometry, if you're familiar with this. So all of it bundles together to really mean a bunch of data. It means we have a base complex manifold, the dependent variables, where the dx acts. We have the corresponding derived object, which is the derived spectrum, or just spec here. I'll write it. So we won't usually write R spec for anything, because R spec will be a terminology for when we're going to take the functor of point, and then we're going to be cofibrantly replacing here. But we can always assume this is going to be cofibrant, so nice. It's a sort of semi-free CDGA object. And so we don't have to do this stuff, at least for this talk. And then we have, so this is the data, and the differential, since we're in the graded world, it acts by a graded Leibniz type rule. And it has the additional, so this would, if we stopped here, this is basically a derived scheme. It has some space, topological space with a sheaf of CDGAs. But we have this extra D-scheme structure, and it's compatible with the gradings, with the derived, with the differential like this. So if you remember last time I said this big bullet means where we are acting through the differential operators. So this is the formally infinite differentiation if we so please to do it that many times. And so it's compatible like this. It commutes with this. This is delinearity. This is, everything is going to be behaving this way. And so in this data, there's bundled together this. So this is a d squared to 0. So we have cohomologies we can take with respect to this differential. So we'll denote them with this h with this lowered d. These are intrinsic to this d scheme structure. And in this data, we have the h0. So this is demanded to be a commutative algebra classical setting. And all of its higher cohomologies, so these are in negative degrees. These are finitely presented H0 D modules. So if you remember, we looked at AD modules with this square bracket. This is the same thing. They're just, this is a commutative algebra, just looks fancy with this notation because it comes from a zeroth cohomology of some complex here or some object. And then we're just looking at it as a classical one, but it's finitely presented. Implicit also in this means we have just a D-linear commutative D-algebra multiplication on the zeroth part. Indeed, it's just a classical algebra. And with respect to this multiplication, we have that these things are the precisely these are the module structure. So more generally, we can take differential graded modules over this algebra of functions on this so-called derived affine D scheme. So these are going to be A module objects in complexes of D modules. So all of that stuff is just exactly what I said last time, these mod AD or A modules in D modules. And this is bundled together nicely by this action by AD. That's why we use this compactified or this compact notation. Okay, so anyways, there's an action. Everything is D-linear. It's also bilinear with respect to this classical algebra part. So the most rough finiteness conditions we want are going to be something again where we're going to be putting this D everywhere. And if you know a certain condition from derived algebraic geometry, it's very, very similar, but it is different in the sense that our finiteness, it doesn't depend on commutative algebraic terms underlying. So if you don't know, in derived algebraic geometry, a lot of the terminology and a lot of the conditions you want are to have some kind of derived enhancement of a classical one, in the sense that there's always this classical truncation functor, and we'll see what it means. It means you have some DG object, and if you take classical truncation, it means you just take H0 of it, and you forget everything else. So you see, if we did that here, we take H0 of all of this, we just have spec D of H, this one. It's just a commutative D algebra. It's just a D scheme, and we forget everything else. We just end up with just this guy. So if we defined some notion of derived D étal maps, it should definitely have in the definition that on classical truncations, it's D étal between the zeroth parts that we saw. It should be the exact definition I gave last lecture. And this is a guiding principle for a lot of properties of morphisms and in derived algebraic geometry that, again, pass through here, but we need to use the module finiteness conditions. So holonomicity is an important one, and perfectness. So the compact generators of derived categories of D modules are the perfect ones. So at least for our setting. So again, so D finite type will be that these are finitely generated modules, all the cohomologies. But we have the additional condition that this is specifically going to be of this D finite type that I showed in the beginning of this lecture. These are coherent sheaf, OX coherent. It's left induced. Take the free algebra and quotient the entry here by some D ideal. We could even make probably another variation of this D finite type by imposing that this has to be finitely differentially generated, but I don't know if this will generate anything interesting or new. Okay, so derived D enhancements are, if you remember this diagram I gave at the beginning, this big pointing to going from one derived schemes down to, or going from D schemes to derived schemes, and showing these arrows that go from sets groupoids to the other one. You have an adjunction that embeds a D scheme into a derived one. So what is that? It's just, as a normal derived geometry, you view a algebra as a complex just sitting there by itself in degree 0, nothing else. And surely this should have an adjoint, and the adjoint is what we already discussed. This is exactly the classical truncation. So you just remembers the 0th part of a D derived object. So this is what I mean by the classical truncation and a derived enhancement. So a derived enhancement is always going to mean you start with some object. There's a DG version that you can get from it. So there's some way you can enrich it. And it has the property that if you take classical truncations of your DG guy, you get the original guy back. That's why it's an enhancement of the original one. So if you take the critical locus that we saw from the first lecture, and you take the derived critical locus construction, taking H0 of this, which is what this is essentially doing, you recover it. So it's indeed a derived enhancement. Just as in ordinary algebraic geometry or derived algebraic geometry, there might be more than one derived enhancement or homotopical thickening. And indeed, this is also, this is possible also in D geometry. So what can we do with these kind of things? Well, for one, the same thing that we get in derived algebraic geometry is we increased our limits, our homotopy. We are formally adjoining homotopy fiber products. So now we have a way that we can do intersection theory with nonlinear PDEs by computing derived tensor products using cofibrant resolutions, or so-called here this degeometric bar complex, or two-sided bar complex. This gives an opening for understanding if you took some field theory defined by some ideal. So let's say magnetostatics and electrodynamics, or no, hydrodynamics, let's say. What do you think the intersection is going to be? Well, magneto or hydrodynamics and magnetostatics together, or electrodynamics and hydrodynamics together, you can try to see these are all various wave equations. They describe different phenomena, but you can start to test do these physical theories have anything in common? And the lack of transversality is captured by these higher tors. This is Serre's intersection formula in the d-geometric setting. It might be interesting to plug in some interesting physical theories or some PDEs here, and then try to see the lack of transversality. Does it compute? Does it tell us anything about, do physical theories have anything to do with each other? Okay, so this is just one new direction you can go in. And now these kind of more neat notation than these CDGA type things, this is always going to just be derived from now on, or I'm infinity categorical. So we've already localized everything. Just it's to put time to put some terminology down. So there's a notion of n co-connectivity. It means that at some point your cohomologies will vanish. So a priori, we just had just D schemes, derived D schemes with just tons and tons of cohomology. They could have infinitely many negative degrees and generators. These are not finitely presented derived algebras in any reasonable sense. So to have some finiteness in derived geometry, you want to have at least this, first of all, this some type of co-connectivity condition. So would they, at some point, the cohomologies that just go away. So it's not going to be too crazy. So this is reasonable. And then you can look at this. So this truncation basically sends an algebra to the same algebra, but let's re-denote it with this t minus n. And this has the condition that if you take cohomologies that pass the n, it's going to be 0. So this is obvious definition of this category. And they're called n co-connective. Now, a derived affine scheme can be made sense to be n co-connective as well, if its underlying algebra is so. And these in turn develop or induce natural embeddings of these categories. And conversely, they have these truncation functors, cohomological truncation at each stage. This is an important structural part of the theory. And they necessarily have right and left adjoints, depending on what we're doing throughout all of this. And maybe I should point out now that in infinity category theory, like because it's extremely difficult to define anything because it's infinity categorical. So if you work with sheaves on prestacks, you can't define what it means for the sheaf to have a value on something. You have to use some other higher categorical thing. So these unstraightening construction or these growth and deconstruction in the infinity categorical setting, which specifies all the data altogether homotopically coherently. Another thing is it helps to define or to be able to first set up a notion on the affines, the derived affines. And then once you have this notion, you con-extend it to higher spaces, prestacks. And this con-extension is, so left and right con-extension are essentially the main tools that I'll just be throwing out randomly here. And they're just higher categorical tools that allow things to be essentially be set up properly. And it's some care is needed to make sure that the functorialities are preserved. Okay, so anyways, this right adjoint is basically taking truncations, and then it's worth noting that you can recover classical stuff this way. Okay, now maybe some fixed n is too much to ask for. So eventual co-connectivity is just at some point. For far enough down the line, your cohomologies will vanish. So at some point, it gets there that we have these finiteness conditions. And as we're taking commutative D algebras, these are naturally commutative monoids in an infinity category of D modules concentrated in degrees less than 0. So we have these free forgetful adjunctions as well that exist. And again, from the D modules, we can further forget the D module structure to O modules, and they are all sort of related together and commute in various ways. It should be noted that when we are using de Rham spaces, something very special happens with the left and right. And here, these D modules are quasi-coherent sheaves on DX, on X de Rham. These are commutative monoid objects that you can obtain from this. And all these functors are very specific. They have they don't always exist as pull and push forwards. And so you need to be very careful. Anyways, we can have more finiteness conditions. So what it means to be finitely presented as algebras, derived algebras. What it means to be almost finitely presented, which means at some point, or it means that your truncations are finitely presented for all the truncations that you have. And then compactness is just a nice term for homotopically finite, basically, in this language. So this can all be worked with. Okay, so going back to the model category one. Now I can give you the promised derived enhancements of some of the classical objects. So these can be checked on, we're working in model categorically now, so you can really find objects and you can compute and you can see these are essentially going to be analogous to computations you make in triangulated and derived categories. So one of them is this solution functors. They are cofibrant. They are derived mapping spaces. So these are simplicial mapping spaces. And essentially, you have to always cofibrantly replace B, unless it's cofibrantly replaced, or unless it's cofibrant already. Typically, you need to also fibrantly replace here. But as I said, all algebras are fibrant for this model structure. It's okay. You don't have to do that. The Verdier duality that we talked about, this local version. So you have the usual D-module Verdier duality. It's an operation that intertwines the derived categories of coherent D-modules. Now we have a local one that intertwines the homotopy categories of the model categories of DG D-modules with coefficients in some DG algebra A. Again, it's some twist by the dualizing sheaf of not the A linear dual, as you would expect. Like I said last time, it has to be the AD linear dual. So this is DG. Everything is DG here. Okay, and you twist and you add the shift by the dimension. So you have the correct functorialities. And you have also a local solution functor. So what is this? This is defined entirely analogously to R sol between D modules. But now we have some different interplaying between the left and rights. So if you remember taking the right and the left, if you dualize it at some point, depending on if your operation is contravariant or covariant, or you need to twist by either one to make sure you get a functor from the left version to the left one, or from the right to the right. Otherwise, you break this sort of symmetry between the left and D right module structures that's happening. So the same thing happens in this infinity categorical world. They're not on equal footing, and it becomes even less on equal footing in the fully derived setting, as we'll see. Okay, so taking the initial D algebra, it's just OX, you actually get this typical, this is the usual D module solution functor I was just talking about. And this is the D module duality, but not the Verdier duality. So we don't need to tensor by the object here, the dualizing sheaf. Okay, so these are just some of the things that we need that will be used to dualize our objects. Okay, so the Collar construction, the D-linear one, as I said, it's just, in the derived world, it's just Collar construction on cofibrant replacement. So in the first slide, I said if we want, or the second slide, if we want to take the candidate for the cotangent complex of an irregular, some spec of some quotient algebra, it's going to be the cofibrant replacement, the differential forms on the cofibrant replacement. So it has a universal properties that can be checked based on the model category structures we saw. Namely, it preserves weak equivalences between cofibrant objects. If it is an honest equivalence if the object is already cofibrant, and you can check a lot more of this consistency. And so it lives in this object category, homotopic category of DGA D modules. And formally, it's just defined in this kind of a way. But if we make a necessary assumption that the cotangent complex, the D-geometric cotangent complex is perfect, or it's a compact object inside the category we're working with. So this is very strong, but we will be imposing further additional hypotheses so we can do this freely. And we'll see that actually at some points we can get it for free from different things. So essentially we want it to be dualizable. Dualizable with respect to the local Verdier, well, derived local Verdier dual that we saw here. So again, if we just took if you forget this part here, we don't get something that we want. We're in the wrong category. So we have to leftify the duality statement. And so we get the d-geometric tangent complex. And what we want basically is the perfectness condition. So this is can be written as a complex of finitely presented objects. Okay, so one of the first results I'll give with my recent collaborators, Arten Shishmani and Xingteng Yao, is that using this tangent complex, it's possible to form the full derived, so full de Rham algebra. So imagine this is just omega 1, so the Kähler differentials. So how do you take wedge powers of this? And how do you get the de Rham complex? This is not a DG question. This is just a regular one. Well, you can just take wedge powers, but the same thing happens by this décalage argument, which is we take shifting. So if we shift by 1 and then take symmetric algebra of this, it's going to be the same thing. So in the derived world, you need to do it derived. So derived symmetric algebra. Okay, this is something that's a bit needs to be done, but the point is that taking symmetric algebra functors can be shown to preserve cofibrant objects or weak equivalences between cofibrant objects. So they can in fact be infinity category, turn into infinity functors, so everything works in this, but it's one of the technicalities. And then derived wedge powers also need to be derived. Wedge powers also need to be derived. So here I'm going to now start to instill the notation of, or the terminology of nice. So for nice enough D spaces, and derived D spaces, I mean here. So you can indeed form the derived version of the variational bicomplex that we saw. So I'll say, so this is 2/3 of one of the theorems in our second paper. So again, this is something smooth. It's a finite dimensional, dx. So you can define following the Pantev, Toyan, Vetselzi, Vacquier, the PTVV shifted symplectic paper. They give this stack of shifted differential forms, and what it means to be shifted and closed in a derived setting. Essentially, it has this space has a filtration. It means it's filtered by subcomplexes. I'm speaking in the derived setting, not this one, because I would have to replace the word complex by bicomplex. So it has this sort of kind of Hodge filtration argument. So it has a sequence of subcomplexes. So let's say the pth version of this filtration of complexes means you just look at the terms in the de Rham algebra that are higher than level P. And you can then define what it means to be closed form. In the pth version of this is some cocycle of degree n. And you can calculate what it means to be closed with respect to a differential in this setting. And one of the fundamental properties or important striking features of derived geometry that don't, if you aren't familiar, is it's not enough to just say d of omega is 0 to be closed as a form, as we're familiar with geometry. So you have an entire homotopy coherent system of relations that must be satisfied. One reason for that is that they have cohomological degrees. You have two things going on. You have two differentials that add together, and you basically have this infinite series, semi-infinite series of forms. And where that semi-infinite series comes from can be seen completely analogously in our point 2 here. So this totalization comes from some kind of negative cyclic homology construction. So we're just totalizing this thing. And these shifts, these means we're shifting everything and putting them in some certain degrees. And so taking our away from the fact that we have at this first point some simplicial space, this moduli space, or this, we're going to pay attention maybe to number 2. And here you can explicitly see what's maybe happening. So in this cotangent complex, we have this bullet point. This bullet point is the cohomological degree. So it's going off in the negative direction. It's a cotangent complex, so it goes into negative degrees. If we dualize it, by the way, if you take the Verdier duality of, let's say, quasi-smooth, so that refers, if you remember, to -1 and 0. If you dualize a quasi-smooth thing, the tangent complex is in 0, 1. Well, essentially, you're flipping these around because it's duality. So this is going off into some negative degrees. And without finiteness assumptions, well, for one, this thing might not exist. So nice enough here is implying this thing exists. And we wanted to sort of not go on forever well, in a general theory, it probably will. And then we have also these powers, these wedge powers, derived wedge powers of this. And this is, if you remember, this is the p degree in the bicomplex. This is the jet degree. So now we have jet variables, essentially, if you think about it, in terms of some, for instance, if you're familiar more with like L-infinity algebras or some chain of bundles over a manifold, you can take a jet construction of this thing. Or if you're more familiar with derived algebraic geometry and you take one of these standard form CDGAs of Brav, Bussy, Joyce, and you take the jet construction of those things, those are, you're taking jets of variables with cohomological degree and weights. And as you're doing this, you're actually getting jet variables with the same cohomological degree. So this is, you have, again, the jet degree keeping track of here, but you also have now it's interplaying with the cohomological degree of the generators. And then you just have the sort of completely underived directions. This is still just coming from the base x, and x is not derived at all. So this is going to be finite, and it goes from 0 to the dimension of the manifold. So the complex is that's a big cube I showed you at the beginning, and we'll see again what it means. But I don't really want to go too much into about the like stackiness and the fact that this is a modulating space for variational K-forms, which means if you have some stack, and if you map any space into it, it's going to compute that object on that space. It's a very standard thing to do in derived algebraic geometry, and but we're not going to talk about that here because I want to be more explicit. So here you can see in this space, an element is going to be a formal sum starting at this term. So theta is cohomological degree n, differential PQ form. And then as you're going up, you're shifting back, and you get some guys coming from inside the page. And then you just keep coming from inside the page. And if you compute this totalization and the differentials, that would be, it's a total differential. So it's a sum of all the three, I'll show you later. It really, you can show what it means to be closed, and it's a bit horrendous. But because I'm not really so familiar with the background of everyone here, and if they know about closed, what it means to be closed in derived algebraic geometry, I didn't really want to present this. This was the third part of the 2/3 of this theorem that I show, is the information for closure of the differential, but I can give an example later. So to prove that this is reasonable and makes sense, you have to show everything is, first of all, compatible with the differential structure. It satisfies homotopical descent with respect to the dA-tau morphisms I haven't mentioned. It's compatible with truncations, respects all the weak equivalences, and all of this can be shown. I mean, it really comes from what I said earlier, is that this derived symmetric algebra functor preserves the necessary structures too. And so if you just zoom in on a little bit, so pick a cohomological degree K. So it'll be a minus, by the way, it's in the, and then so we're going to look at the PQ part. It's a tricomplex, just one term, it'll be zooming out like this. but this one is coming out of the page. This is the derived one. The vertical is here. It's increasing the Q jet degree. This is increasing the horizontal degree. Okay. So again, you can define it and then say what it means to be closed in this, and an n cocycle. So that's what this big Z means. It's taking a cocycle with respect to a total differential. So again, here's all three. I want to not say so much about this because I think we only have about 15 minutes left, and I really want to go to the D space or the Durham space version too. It's quite to talk about the same type of objects, cotangent complexes, but on solution stacks. And it's going to be helpful in computing actual tangent complexes in perturbative field theories. So system algebraic structures that exist, there's a bi-graded CDGA structure going on. Well, it's actually a commutative algebra objects in graded mixed bicomplexes. Doesn't matter what that means at all. But if you look at the fixed gradings in all three, it just acts as you would expect. And so again, this is what the tricomplex looks like. So we have a triple grading. P is so here I'm writing P now as it's in N, so this was supposed to be the horizontals. So this was Q before. So anyways, the horizontal one goes from 0 to the dimension. The vertical jet cartan, those are all different terminology for it. It's the vertical one goes infinite off forever because of the infinite dimensionality of the jets. And then you have the derived one. And so we're working with connective CDJs, but it might be the case that there are PDEs that somehow contain these or maybe I should have written it as stacky to take out this connective, some stacky degrees of freedom. It means it has some positive thing. So this is a possibility, but I haven't thought about it. So the example really quickly is that if we want to compute degree 0 closed forms on this, k equal 1, or degree 0, so 0 shifted 1 forms, and the closure for what this means. So as I showed you from the theorem, you have this formal sequence starting with the degree of the form. So before it was a PQ form that we started with. That's the first term in the huge thing that in derived geometry you call a key. So here PQ is 1. We're not using the bicomplex structure right now. We're just looking at 1 forms. And let's say degree 0. And then using this negative cyclic homology type construction, whatever that means, you come out and it just asks for decomposition like this, and you compute the differential. So it acts kind of like going off. This keeps going off, and you can kind of add it up. And here I'm not showing the other degree. So this is a bit all vague, but you can actually, what our form looks like this, starting to look like this. So what is this? Each j and minus I is a j form in a cohomological degree I. So I is now positive integer because I've already put the minus here. So to be closed, you can compute what it means specifically, and you get, first of all, you get closure with respect to cohomological. So why is that the case? Because I declared that we want to be looking at form degree 1, cohomological degree 0. So of course this is going to be 0 because I said our CDGAs are concentrated in degrees less than 0. So we don't have anything in positive degrees. It kills it. And then the closure is this sequence of cohomological or homotopy coherent systems of identities. And this can be seen. So this is actually exactly what you get in the derived setting as well. These kind of closure of all of these. But what's different is that we actually have that additional bicomplex structure that splits this J. So let's invoke that now. So because we have this forms, the bicomplex, each of a different cohomological degree splitting, we can now look at all the contributions, and there's a huge system of equations, and we pick the bicomplex degrees that equate with each other and then look at them as different systems of equations. So in Derived weight 1, what does that mean? That's just this one form, degree 0. So we have the two contributions. It's a one form in the horizontal degree, and it's a one form in the vertical degree. And so this equation of just being killed by the the cohomological differential reads as so it splits into a sum of the two. So this thing now looks like this one. But these live in separate bicomplex degrees. One's in 1, 0, one's in 0, 1. If you look at some paper, let's say like a graphing paper, and you put dots on it, these are different. They lie in different columns in different rows. So you want to line them all up, and then you want to equate everything that you get. So these ones don't line up. So they're different. They're independent systems. So you just have 1 degree 0, 1, 0 form killed by the cohomological differential. And the same thing here, 0 and a 0, 1. Okay, Derived weight 2. This is a 2 form. So again, you could just exhaust the possibilities. 2, 0, 1, 1, 0, 2. Now you have the similar relations that you see from derived geometry, like dH and this one 0, dV and this one 0. The difference being we have this third one, which is a mix of the three, and these are all degree in cohomological degree 0. Note you see this is in degree -1, but it's a cohomological one, so this becomes degree cohomological degree 0. And then you can do it to Derived weight 3 and so forth, so on and so forth. So this is just a very simple example where we can start seeing like there's a huge amount of equations that are satisfied. So it remains to be seen if there's intuitive meaning for these higher fields. So one of the first variational tri-complexes that was described in the literature was not derived necessarily. It was a mix. I think it was due to Hanno and Teitelboim maybe about quantization of gauge systems. And they combined this causal Tate structure with the bicomplex one. So they did get a tri-complex. And this is actually reminiscent already of the derived structure. As I said, it's a part of the cofibrant replacement. So they basically took a KT resolution of the on-shell field observables. And then they're like, okay, so they called these like cohomological minus terms. I think these are ghost terms of -1. So in this way, you can see that these might be higher. These might have meaning in physics as like higher fields with higher antifields, higher ghosts, and ghosts of ghosts, anti-ghosts of whatever. I don't know the physics terminology, but it would be interesting to see this further. So this shows that this their variational tri-complex appears in the larger realm of derived variational tri-complex. Okay, so I'm going to skip over the characteristic varieties in this one. Essentially, it's just we now have a tangent complex, so put it into the formulas we saw before, but you need to be careful about the fact that taking the support or taking this the support of a complex is the union of the supports of its cohomologies. And essentially, you can just get the non-micro characteristic varieties in the derived setting. The big point about this is if we have a cotangent complex, if it exists, we can pull back along a solution. So mind you, this is in the Kähler forms for an AD module. So what is A? A was functions on spec, well, the D space. So tensored with D, this looks like functions on a product of spaces. So what's the space that has its algebra of functions, the sheaf of differential operators? It's a bit unclear, but the point is, once we have a solution and we pull back an AD module, we're pulling it back to X. And what this does is it removes a dependency on A. And so this is a D module. And so you can ask when this complex pulled back along a solution, this is formally the linearization, derived linearization along a solution that we saw earlier. Now it's using complexes. And you can ask this to be elliptic as a D module or a complex of D modules. And so it can be seen that condition I said earlier in that little example at the beginning, the one I showed you is really, that's what it means to be elliptic as a D module, is this condition. Means you have no real characteristics. And so this, you can then go through the same thing, and now we have when a nonlinear PDE is elliptic. If you take the resolution, so you take the cofibrant replacement of this algebra. So these are not derived, these are just classical. You take the candidate for the derived, the tangent complex. So it's again, on the cofibrant replacement. You pull it back along the solution. You do this U thing. This was micro-localizing, by the way. So it's just tensoring with something, some sheaf of functions in some cotangent bundle or some normal bundle. And you ask that this holds for all the solutions. And then you can even do a bit more solution independent one. And it's asking for this larger thing. And now we have a way of saying, oh, when a pre-stack is elliptic. It's elliptic again, and you can make sense for all solutions as well. So this is unimportant. And I'm just going to now zoom through in the last 5 minutes a Derived space approach, which I think is important because it highlights some of the significant differences that the two theories have. So even though that quasi-coherent sheaves on X Derived are D modules, in the derived world, this isn't really the same thing. They're developed together in conjunction with formalism of something called ind-coherent sheaves, developed by Gates-Gorey and Rosenblum in their two fantastic books about derived algebraic geometry called A Study in Derived Algebraic Geometry 1 and 2. So ind-coherent sheaves, as the name sounds, it sounds like an completion of coherent sheaves. It's not quite, but it's very similar. And so it has a lot of similarities, but it has a lot of nice functorial properties. In this theory, these infinity categories, so they're developed together, quasi-coherent and ind-coherent together. So you have this map from P Derived, so X, so every space, not necessarily a smooth manifold or smooth, some smooth space. These can be derived pre-stacks. So you always have this. And if you take quasi-coherent sheaves on X, this is just ordinary quasi-coherent sheaves on X. So if you take Q-co, push forward and pull of this thing, you end up with quasi-coherent sheaves on this one too. These play the role of left D modules, whereas ind-coherent sheaves are known to play the role of right D modules. And the difference being, I guess, between D modules and distributions type thing. Okay, so in any case, this functor has, or this map has it has a sort of push forward. This is called the Weil restriction or derived Weil restriction. It's a way of, and this plays the role of the jet functor. So we're pushing something to live over Derived space. That's saying, okay, we're giving it a categorical connection that we saw earlier. Well, this actually, depending on the properties of this spaces, they're derived argent stacks, for instance, then this push forward functors, and they'll have adjoint functors in different ways. And in any case, we have this adjoint pairing, P Derived push forward, P Derived pull back. And so these define a monad or a comonad here from pre-stacks to pre-stacks, and we'll call this the infinite or the derived jet space. So it's a lower star, upper star. And an object in the essential image, so this is all infinity categorical and derived. It's a derived jet pre-stack. And what can be declared as a derived nonlinear PDE on E. So sections, this is what I mean before when I said sections, this is just some pre-stack object with a map to base. It's some subspace. Okay, be careful in the derived world what do you mean by subspace, but it's unimportant for now. And so it's a subspace of this derived jet space. Okay, so as a infinity categorical junction, it has some nice properties. One of them being that there's it has a comultiplication, and also you can take derived sections of these spaces in the same way we took sections before. But now instead of taking the sections of D schemes, you're taking derived mapping spaces relative to the Durham space. So I'm just writing them here really quickly because these are two facts that are important. The first one means we're taking flat sections. So it means we're taking the horizontal sections of, so those that are mapping out of the Durham space into the jet bundle, they map into this one. And this is basically a way of identifying those sections or solutions. So remember before I said there's this way to define solutions as pull back from the Durham space. That's what this is doing. And these are derived spaces of sections too. So you have to be careful with this. And also you can show that there's an equivalence as well, that this R sol, which I'm about to introduce, it means the derived spaces of solutions and derived sections are the same. This is the derived way of saying formal solutions, like formal prolongation is formally solving the PDEs. Okay, so derived solution stacks, and let's finish in 1.5 minutes. So a morphism of pre-stacks is a flat section if it's attained by pullback. So by this pull-push type thing we just saw with this P Durham star down, or lower star and upper star, it fits into this kind of a diagram. And so if you're taking a section here on the right, it's declared flat, or the one on the left is declared as a flat section if it's pulled back from here. So by abstract nonsense with some kind of functorialities with mapping stacks, you get some natural transformation induced by this. And if we let Y be a PDE in the setting that we just defined it as, then it has a derived mapping stack of solutions. So this is what this R sol that's written a bit like a child who just got their hands on crayons with this weird large L. It's taking flat sections over the Durham space. And remember, we wanted a PDE to have solutions if they factor through this embedding from Y to the jet space, and this can be made precise. Okay, here's where finiteness becomes extremely important. So we have basically just working with arbitrary derived spaces so far, without any derived terminology. Usually what people would want is at least that they're locally almost of finite type. So in derived terminology, people call them LAFT. So LAFT. Okay, so LAFTness implies that these we can have certain adjunctions that exist with incoherent sheaves and quasi-coherent sheaves that are very nice. But we also have no guarantee that these spaces have any kind of cotangent complex. They might not even admit one. They might have it and it's not dualizable. It might be so we need to be guaranteed these things. You need to probe further into some finiteness conditions. And to do infinitesimal geometry, the term that comes up really is called admits deformation theory, or it's simply def. So the nice pre-stacks, according to Gates, Gordy, and Rosenblum's book, are called LAFT def for short. So something similar happens here. For an arbitrary space, pre-stack over this. So these are now the versions of PDEs that we're looking at because they're space with a connection. The most prototypical one is jet spaces or their subspaces in the derived sense. It's unlikely we can do anything with them at all. And by that, I mean, we can't take cotangent complexes. We can't try to build derived Durham algebras. Nothing will behave well, or we can barely even use their any sort of local structure. So here, nice is always going to be this kind of LAFT depth thing. So even if this is LAFT, the jet guy, the push forward, the Weber restriction is not going to be. But if even though it's not, this R sol associated to it, it sometimes actually is, which is a bit strange, but it means that sometimes solution spaces behave in the derived world somehow a bit nicer even. Well, not nice, maybe this is the right terminology, but it means we can get a hold on these by making restrictions of finiteness hypothesis on these objects. So just to end, in our first work, we made these finiteness hypotheses called definitary. And what definitary basically means is whatever our original space is, it's going to admit a cotangent complex. And it's not important that this space itself is LAFT def. What we want is that the solution space that we are interested in doing formal geometry of in the and working with these derived moduli spaces of solutions, this is the one that has the nice properties. And so you can prove that with these assumptions that it indeed restricts to these between these nice categories. So and what this is importantly telling us is that if this space is nice, this space is nice when it's evaluated on a nice object, and the initial object that we take is nice in its own right. In its own right. So what's important here is you can probe these spaces for the functor of points approach. And I know I'm over time, I'll just finish up in 2 minutes, is so you have this adjunction dualities between the two. You take a U point of a space. It has an evaluation. A U point is just, you evaluate by the functor of points, this R sol, that's why it's underlined on a point U. These are going to be always locally, like very finite derived spaces or something else. These are our probing spaces, and this, if you just, a point in this is the same as a point in the mapping stack. So if you remember what the mapping stack looked like, I can't find it. This one, exterom times U to Y, it really is some kind of evaluation. So we're going to write it as J infinity to be with the same kind of notation as before. So by adjunction, you can build these diagrams. And if you have a PDE, you get it like this. And as per our conventions, the solutions to the PDE are the ones that are going to somehow factor home through this R sol jet Derived. So with the niceness conditions and using standard push-pull constructions for derived mapping stacks that are very common in derived algebraic geometry, you can compute what the derived cotangent complex of derived jets, a derived space, linearized around a solution looks like. It's in terms of, you can write it like this. So here, the sheaves is really too vague. This is not, these are very special types of sheaves. They're incoherent sheaves. Actually, these are covariant objects, so this should be pro-coherent, or some pro objects, or derived Tate spaces, or derived like ind-pro complexes. So the duality goes between ind-co and pro, because when you dualize, so you have to be really careful in this infinite categorical setting, and double dualizing is also not going to give you anything back that you started with without very strong and important hypothesis. Okay, so just playing around how that kind of proof looks, you just have all these objects in here. You can take the relevant sheaves. Also, I'm writing star and star to be economical with notation. These are typically not the stars you would be thinking. And so you can show that this is well-defined. And going one step further and then ending is you can, instead of just taking any, you can sort of generalize this and not just take a, so if we took, we took maps out of exterom into some derived deep PDE, but exterom is just the identities, it's just exterom space over itself, it's just the identity. So it's itself an object of pre-stack over exterom. So we can then say, let's take solutions with values in any other Derived space. And it looks like this. The question then of this mapping stack, a more general one to possess cotangent complexes and compute it, is more subtle, but it goes around the same arguments, but with additional hypothesis about the finitariness of the operators or of the objects. And again, you end up with some kind of like push-pull construction by evaluation by taking a U point of this stack, and you get some expression. And it can be shown through our previous computations, if this is now taken to be jets, that this is E. And with some, if you make those nice assumptions, it really means something admits deformation theory. But we can also make the hypothesis admits deformation theory relative to some Derived space, because this has none. And so this is really some kind of relative. So if this was jets, in our previous slide, we saw this was jets of E. It becomes then computed in terms of E, but if for the reasons I just said, this will actually become E over X. And what is that? That looks like vertical, the derived version of vertical differentials or vertical forms. So if we can dualize this thing, that's exactly the tangent, the solutions to the linearized differential equation we saw in the geometric linearization setting. They were vertical vector fields that preserve, that are pulled back along a solution. And so this is a derived realization of this phenomena based on finiteness hypothesis of these spaces. Okay, and then you can just do something more general, and using the fact that differential operators are from a stack E to F, or even sheaves E to F, are the same as D-linear morphisms from jets of E to jets of F, and using a junction. So remember, this is jets infinity of E to Q. That's just an infinite order differential operator out of jet spaces. If you just use a junction, move it over, this is same thing as differential operators. So this is one way you can compute constrained systems in homogeneous ones. And using the very, very similar techniques again, but again, with so many hypotheses on finiteness and it's very careful, we can study cotangent complexes, mapping spaces, and go from there. Okay, so I feel like I should stop. I've gone a bit over, but yeah, so this area is very, we hope that you can use these by plugging in various higher stacks that we know model things in physics, and use these to study higher categorified sheaves of categories on these derived R souls and these solution spaces, and use techniques from PDE theory to understand them. One example, really quickly, is if you take in this way, R soul of X around wherever it went, this guy here, if you took this to be jets, but jets of what? If you just take X itself and let X be smooth, and then you take X cross a point and you take the point quotiented by some algebraic group, it's possible to show R soul of jets of that guy that I just said. This is the same thing as the mapping stack from X durum to the classifying space of that group G. And so what's that? That is the moduli space of flat G bundles on X. And so in this way, we can see that, well, plugging in things here, using PDE theoretic techniques by taking jets of spaces of stacky sections or stacky objects, we can find the moduli space, for instance, in this case of, say, Chern-Simons theory in a derived stacky way. And now we can try to do physics with these things. Okay, so thank you very much for your time. I apologize for overdoing it.